Previously, we covered the core foundations. Now in Part 4, we tackle what is the Veil Nebula and why does it look like that? Part 4. What will it look like in the future? What is the Veil Nebula and why does it look like that? Mount. Part 4. What will it look like in the future? Hook. The Veil Nebula looks spectacular right now. But right now, in cosmic terms, covers tens of thousands of years. What we're seeing is a brief chapter, and like all chapters, it has an ending. Intro. In Part 3, we looked at what the colors in the veil actually tell us, the chemistry and physics baked into those glowing filaments. This time, the question is simpler to ask, but harder to sit with. What happens next? Specifically, how does the veil change from here, and when does it effectively disappear? Section 1. The blast wave is slowing down. The veil's structure is driven by a blast wave, the shock wave from a supernova that detonated somewhere between 10,000 and 20,000 years ago. That wave is still moving outward, but it isn't moving freely. Every time it sweeps through a pocket of interstellar gas, it picks up mass. And as the wave accumulates mass, it decelerates. This is basic physics. A snowplow moving through heavy snow slows as it pushes more in front of it. The veil's blast wave is doing exactly that, just on a scale measured in light years per 1,000 years, rather than meters per second. As the wave slows, the thin, bright filaments we see today, produced by sharp compression at the shock front, gradually broaden. The temperature difference between the shocked and unshocked gas becomes less pronounced, the emission weakens, the lines blur. Section 2. Fading, not sharpening. This is the key point. The veil won't grow crisper with time, it will grow fainter. Over the next several tens of thousands of years, the shock front will continue to expand. It will reach diameters significantly larger than the roughly 110 light years it spans today, but the energy is being spread across an ever-growing volume. Surface brightness drops. The filaments that currently require a large telescope to resolve properly will require a larger one, then a larger one still. At some point, and this threshold is difficult to pin to a precise date, because it depends on exactly what density of gas the remnant encounters, the veil will drop below the practical limit of detection. Not because it's gone, but because it's too diffused to distinguish from the general background of interstellar gas. Section 3. What it leaves behind. When the blast wave finally stalls, what remains isn't nothing. The expanding shell deposits energy and material into the interstellar medium, the thin gas that fills the space between stars. That material includes elements forged in the original star over its lifetime, and heavier elements produced in the supernova explosion itself: oxygen, sulfur, iron, and others. Those elements don't disappear. They cool, they drift, and over millions of years, they become part of molecular clouds, the dense, cold structures where new stars form. There's genuine scientific basis for saying that the atoms dispersed by a supernova remnant like the Veil can, in time, end up inside a new star, or its planets, or whatever forms around it. The Veil isn't just dying, it's contributing to what comes next. Closer. What makes the Veil worth understanding isn't just what it looks like. It's what it represents. A single violent death stretched across tens of thousands of years, seeding the galaxy with the ingredients for everything that follows. We're seeing one frame of that process, a particularly photogenic frame, granted, but still just one. Part 5 takes up the next key question about the veil, and there's more to unpack than you might expect. If you're finding this series useful, subscribing means you won't miss the rest of it. End card. That is Part 4 of What is the Veil Nebula and why does it look like that? In Part 5, we explore the next key question. Subscribe so you do not miss it.